Morning all, and we have counting function part 2, and here we'll be discussing advanced level and little bit hard level problem. If f has exactly 4 elements in the range, second part is f of f, which is composition of function, has 4 elements in the range. So let's deal with the first part first. So I've set a1, a2, a3, a4, a5 operating to the same sample set 3, a4, a5. If you want 4 element as the range, let's say a1, a2, a3, a4, we have to leave one of them. So in how many ways we can leave one of them? 5c1, or I can select 4 element in 5c4. Now once I've done this selection, the next part is to map the input to the output. So it might happen like a1 is going to a1, a2 is going to a1, a3 to a2, a4 to a3, and a5 to a4. There can be many mapping, but it has to be exhaustive mapping. So all these 4 elements must be exhaustive. Now how to go about it? Of course you can use the principle of inclusion exclusion, which was discussed in part 1 of the lecture, to find this, but there is a smart way as well over here for this particular case. We can clearly see a1, a2 is going to a1 and the remaining is going to one element H. So I can treat as if a1, a2 were one block. So it's just a bijection between new x and a new output. So we have a1, a2 going to a1, a3 going to a2, a4 going to a3, and a5 going to a4. So in how many ways I can select 2 of them, because definitely exactly 2 of the input will go to one of the output, okay, for every element to be exhausted. So out of 5 I can select 2 of them. Once I have made these selections, now so I have a group of 2 objects, one object, one object, one object, and in the output set I have 4 objects, and this is just one-to-one mapping. Okay, so how to go about it? Now suppose if the second set, so this is first set, second set, and third set, of course all of them are identical. If it contains exactly 5 elements, then can we have f of f as 4? Clearly no. So let's say if a1 x to x must have the same 5 connection, because a1 is going to 1, 2 will go to 3, 3 will go to 2, 4 will go to 5, and 5 will go to 4. So clearly in this case, number of element in the final set, let's say this is x, I'm calling this y and g for the sake of distinctiveness, will be still 5. So it's not possible. Hence the set y cannot have all 5 elements. I'm denoting this symbol that of x kind of is cardinality of set A, means number of elements in set A. Okay, so what are the other possibilities? Of course the next possibilities will be if the second set y contains exactly 4 elements, so a3, a4, a5. So now if it contains 4 elements, let's say 1, 2, 3, 4, and 5 is left. So of course it's possible, because Z will also contain the 4 element. So let's say one of the mapping is something like this. Now as we know, none of the elements is mapped to A5. So clearly A1, A2, A3, A4 will also be mapped to A1, A2, A3, A4. We don't have any mapping of A5. In this particular situation, what kind of mapping we'll get? We know since A1, A2 is mapped to A1. Okay. So A1 will be mapped to A1. A2 is also mapped to A1. So if I make A2 map to A1, A3 is mapped to A2, A4 is mapped to A3, okay, and A5 if I don't map. So of course here A4 is left. So it's not possible that the function from y to z is many one. So that's not possible, because if it is many one, again the number of elements in the range is 3. So what we have noticed is set y must have 4 elements, at least in this case. I'll also check the possibilities for 3 elements. That is automatically discarded, because if set y is having just 3 elements, let's say a1, a2, a3, so set z still cannot have more than 3 elements. So maximum element of set z will be 3 if set y is having 3 elements. So in that case again the range will not have 4 elements. So that's gone. So the conclusion is set y must have exactly 4 elements. in total. Okay, under that conditions, and so the conclusion is set Y must have exactly 4 elements, and backed up with the idea like a set from Y to Z must be a function from Y to Z. So the conclusion is set Y must have 4 elements, and the function from Y to Z must be a bijection. It must be 1 and 1 2. So once this is clear, we can simply count the number of such functions: A2, A3, A4, A5, A1, A2, A3, A4, A5. Now we know, suppose if I leave A5, so A5 will be left in Z set also. So I could have selected A1 to A4, 5C4 ways. Once I have selected this, I have a way to map them. Okay. In how many ways I can map them? Let's say A1 goes to A2, A2 goes to A1, A3 goes to A4, and A4 goes to A3. So once this is done, we don't have a choice on set A because A1 is going to A2, it's the same function. So X to Y will also get mapped with the same bijection. So A1 must go to A2, A2 must go to A1, 3 goes to 4, 4 goes to 3. Now what about A5? What about A5? For A5 we have many choices because A5 can go to either A1 or A2 or A3 or A4. So now the situation is quite clear. We have 5C4 to select the elements from Y, and the number of functions which operates from Y to Z, because A5 will already be rejected in set Z as well, so that will be 4 factorial. And for A5, because from A1 to A4 we don't have any choice. Once a function is established from Y to Z, the same bijection will be there for X to Y. So for A5, again it will have 4 options. So this is the answer to the second part of the problem. I hope you have enjoyed the problem. In general, if we have n elements in set X, so we'll have n c n minus 1 into n minus 1 factorial, and again for last element n we'll have n minus 1 choice, which contains 4 elements 1, 2, 3, 4. Of course, I can generalize the problem for more elements. First, let's solve this specific one. We have to find the number of functions f so that f of x is x. Now clearly one of the wrong answer that we'll get is just 4 function, because some of you might think, let's say f of 1 is 1, f of 2 is 2, f3 is 3, and f4 is 4. If this is the case, clearly it satisfies f of x is y, because f of 1 will be f of, and f of 1 is 1 with respect to 1. Similarly, all f of I will be I, or all I belonging to 1, 2, 3, 4. So it feels the answer for this problem is 4, which is clearly wrong, because there can be other possibility as well. Let me talk about one such possibilities before we go and hit this problem. 1, 2, 3, 4, 1, 2, 3, 4. It might happen is 1 is going to 2 and 2 is going to 3 going to 4, 4 is going to 3. Under this condition also we have f of x equals x for all elements. For example, f of 1 is f of, and since f of 1 is 2 and f of 2 is back to 1, so it's correct. What about f of 2? Since f of 2 is 1 and f of 1 is back to 2, so you can see f of I is. What about f of 3? f3 is 4, but very smartly I mapped 4 again to 3. And the last one, f of 4, f4 is 3, and 3 we have mapped back to 4. So this is also one of the possible functions. Can you think of more such sample structure? Of course, here we could have given 1, 2, 3, 4, 1, 2, 3, 4. I could have grouped 1 with 2, 2 with 1, and made 3 with 3 and 4 with 4, right? So clearly f of 1 will be still the same as the second case, f of 2 still same as second, and f of 3, since f3 is 3, back to 3, and for 4 same situation. So now you have recognized what's happening. Okay, let's also consider, suppose instead of this, if I map 1 with 3 and 2 with 1, 3 with 2 and 4 with 4. So is this a valid combination? Let's check. So what about f of 1? So this time f of 1 is 3, so this will become f of 3, but f3 is 2, so that's not possible because we want f3 to go to 1. Okay, so one thing is clear, is I have to make a group of either 2, 2, or I have to make a group of 2, 1, 1, these kind of structures, because if 1 is going to 2, 2 has to go to 1, we don't have a choice under the restriction f of x equals x. Okay, for instance, if 1 is going to 3, 3 has to go to 1, or maybe I'll just map 1 with 1, 2 with 2, 3 with 3, or 4 with 4. So understood this? So having gained this basic idea, now we are ready to hit the problem. So we have only two possibilities. Possibility is 1. It's 1, 2, 3, 4. 1, 2, 3, 4. So make a group of 2 objects. Or we make a group of 2, 1, 1. Okay, make a group of any 2 objects. Once I make a group of these 2 objects out of 4, so partitioning it into 2 zones, 1 has to go to 2, 2 has to go to 1. Okay, 3 will go to 4, 4 will go to 3. If it is single, then 1 going to 2, 2 going to 1, and we can have 2 going to 3 going to 3, 4 going to 4. Or we can have clearly set where each of them is going to their fixed point. So make a group of single. 1 is going to 1, 2 going to 2, 3 to 3, and 4 to 4. Let's count the number of such possibilities for this. So as you can clearly see, when we have 1 and 2, okay, so the other choice is locked because 1, 2 going to 1, 2 is already taken here, right? When 2 elements are single. So I'm making a group. It means those group elements should not go to their fixed point 1 and 2. Now in how many ways I can make a group out of 4 objects, 4 possible objects, 2 each. So that's very simple. So we have total 4 objects, select 2 of them, and from the remaining 2 select 2 of them. Since group size is same, because it might happen 1, 2 I have selected first, and then 3, 4, or 3, 4 I have selected first, and then 1, 2 so I will divide into 2 factorial. Okay. Now once I have selected the group size, there is only one way in which 1, 2 can go to 2, 1, or 3, 4 will go to. So from here we got 6 by 2, which is 3 total number of cases. Let's come to the second possibility when we have a group of 2, 1, 1. Second, out of 4 I'll select 2 objects, and from the remaining I'll select 1, from the remaining I'll select 1. Now again, this consists of the case when 1, 2, 3, 4 is selected, or 1, 2, 4, 3 is selected. So that's basically same group selection. So division into groups, hence we have to divide by 2 factorial, and that gives answer as still 6. Now into once I have selected group, there is no way because 1, 2 has to go to 2, 1, and 3, 3 will go to this. So we have 6 possibilities over here, so which gives you 6 as the answer. In the last case, when we have 1, 2 is going to 2, 3 going to 3, and 4 is going to 4, we have only one possibility. Is the total number of answers that we are getting is 10. So I hope this is clear. Now of course you might ask the question, what will happen if the number of elements in the set is more, right? So still we can use the same method, or we can use even recursion to kill the problem. So let's try to kill the problem in a recursion way. Okay, so in general, suppose set A is having n element 1, 2, 3 till n, and the function operates from A to A. Now I want f of x to be x, where x is an element of set A for all x. Okay. So now we want f of x to be x for all x belonging to set A. Suppose the number of such functions here, let's call n. What is n? is number of functions from set A to A such that it follows the guardianship given above. F of x equals x, which means f of 1 is 1, f of 2 is 2, and so on. Now what will happen if we are going to add a new element to this set? So let's try to compare this set with a new addition. Let's say if I'm adding n plus 1 element, so one more object in the set. Okay, so now the new set will be an plus 1. So it's like number of functions from set. Of course, B to B you can tell such that f of x is x. So now somehow we need to relate an and an plus 1. Now by adding new element, what has happened? We have only two possibilities. What are the possibilities? Either this new element n plus 1 will go to itself n plus 1, right? So if I'll see, now we have 1 2 till n plus 1 and 1 2 till n plus 1. So how many such functions are there which satisfy f of x equals x? So we have only two possibilities here. Either it might happen like n plus 1 is already locked with n plus 1. Then the remaining problem is just about finding number of count for f of x equal to x for n elements. It might happen like n plus 1 is going to just n plus 1. So under that case, it's just number of functions having n elements, because this is already locked, and the remaining 1 to n is back to the same problem. What will happen if n plus 1 is not going to n plus 1? So let's say n plus 1 goes to 1, suppose. Now in this case we don't have a choice because 1 has to go to n plus 1. So if n plus 1 goes to 1, that automatically guarantees 1 going to n plus 1. In this circumstances, we are left with still 2 to n and 2 to n. So that is back to a n minus 1. Right? So that is back to number of functions containing n minus 1 object and following the same guardians. But n plus 1 was having how many choices here? N number of choices. It could have gone to 1 or 2 or 3 like this till n. So in total possibilities in the second cases, if it goes to 1 we'll have n minus 1 case, if it goes to 2 we'll have n minus 1 case, if it goes to 3 we'll have n minus 1 case. Like this, if it goes to n we'll have n minus 1 case. So how many n minus 1 case will come? It will be n times n minus 1. So I can tell the total number of functions with n plus 1 element is an plus 1, that equals to an plus this case plus this case plus this case n times. So this is our recurrence relation. What's the beauty of this recurrence relation? Is once you know a particular value, you know the next generation. So let's say if I keep a1. So what is a1? Clearly a1 is 1, because if you have one element, the only way where f of 1 is 1 is when f of 1 is 1. Okay, there is no other way. What about a2? a2 is also easy to calculate. If you have got two elements 1 2 and 1 2, we have only two possibilities. One possibility is 1 going to 1, 2 going to 2, or 1 going to here. I can easily tackle the next part of the problem. So if I'll in this recurrence relation, if I keep n equals 2, so I'll get a3 equals a2 plus 2 times a1. Similarly put n equals 3, so a4 equals a3 plus 3 times a2, and which gives me answer for a4 very easily, because a2 is 2, a1 1, that will give 4, with a3 4 and a2 2, we have 6 plus 4 10. Now the beauty of this recurrence is I can find even the next generation. Let's say a5. a5 is obtained by putting n equals 4 in that recurrence, so that gives a4 plus 4 times of a3. Now a4 is 10, a3 is 4, so that will give 26. So using this recurrence you can find any values. I hope you must have enjoyed the method, and this was a great way to solve this problem. Now one more question for you to ponder anything. In the same question, let's say we have 1 2 3 4, which is set A. 1 2 3 4. the function operating from A to A. This time we want f of x equals x. So how many such functions are there? Of course, one of them will be when 1 going to 1, 2 going to 2, 3 going to 3, and 4 going to 4. Can we think of one more functions before it actually hit the problem? 1, 2, 3, 4. Yes, it's possible. Let's say if 1 goes to 2, 2 goes to 1, and 3 goes to 3, and 4 goes to 4. Is it possible? That this will also satisfy the relation. Let's try to check. So clearly f of 1 is 2, and f of 2 is back to 1, and f of 1 is 2. Right? So this is not happening. 1 goes to 2, 2 will go to 1. And then again 1 will go to 2. So this kind of mapping is not possible. Then what are the possible mapping? Let's try. 1, 2, 3, 4. 1, 2, 3, 4. Suppose 1 goes to 2, 2 goes to 3, and 3 goes to 1, and 4 goes to 4. Now is this possible? Let's give a try. f of 1. So f1 is 2, f2 is 1, and f1 is 2. So that's also not possible. Sorry. And f1 is 2, and so hence f1 is 2, f2 is 3, and f3 is 1. So let's give a try on f of f1 with f1 2 and f2 going to 3 and f3 going back to 1. Yes, it's possible. So I hope you must have got a hint. So still now you have to make a group of 3 object, and in that 3 object it's not possible like 2 of them is just mapping to each other and 1 is left. So we can't have a single connection, the fixed connection. So once you have made these 3 object, 1 will go to 2, 2 will go to 3, and 3 will go to 1. Or it might happen is 1 is going to 3, and 2 is going to 1, and 3 is going to 2. So like this you can consider all the case, and we can do the problem. Okay, so I urge you to repeat the questions for f3x, f4x. f4x means f of x, and so on and so forth. You can even think of a recursion formula in the same manner as I have done above. So now the conclusion is, yes, for f of x equals x, for a limited number of objects in the set A, I can directly do counting. For more number of objects, I can even use recursion. Even if instead of 2 composition, we have 3 compositions or 4 compositions, the situations can be handled with the same physics. Okay. Let's move to the next interesting question. Now this time we want f of I should not be I for any I belonging to set S. And let's say set S contains 1, 2, 3, 4 objects. I'm giving you all examples for just a smaller sets. Of course, the idea is valid for any n number of sets, right? So what we want is f1 should not be 1, f2 should not be 2, f3 should not be 3, and f4 should not be 4. Give a try by yourself and try to find the number of functions operating from set S. So the first part is very easy, because if you have 1, 2, 3, 4, 1, 2, 3, 4, I have not mentioned whether the function is 1, 1 or anything about that, right? So that makes the problem easy, because 1 cannot go to 1. So how many choices is there for 1? We'll have 3 possibilities. So 1 is have 3 possibilities. Similarly for 2, it can't go to 2, so 3 possibilities. 3 cannot go to 3, 3 possibilities. 4 cannot go to 4, so 3 possibilities. So to that 3 to the power 4 is the answer. Now in this answer, it is not necessarily 1 function, because it might happen is 1 is going to 2, 2 is going to 1, 3 is going to 4, and 4 is also going to 1, right? So these possibilities are there. Okay, now the second part of the problem is, what if the function is also 1, 1? Now here, since we have equal number of elements in set A and set B, because set B is same as set A. So whether the function is 1 1 or function is onto, it means the same thing here effectively. Okay, so find the number of bijective function. I can tell you either 1 1 or onto, or both 1 1 and onto represents the same thing. So that will be a bit difficult and challenging one, because now what we want is every element has exactly one image. So clearly in this condition, if 1 goes to 2, okay, so it's possible 2 goes to 1. Now 3 has to go to 4, and 4 going to 3 is one of the possible answers. Can you think of other possible answers? Clearly, yes, 1 going to 4, 2 going to 1, maybe 3 going to 2, and 4 going to 3. So now again, this boils down to a principle of inclusion exclusion. In what sense? Now we don't want 1 to go to 1, 2 to go to 2, 3 to go to 3, and 4 to go to 4. So total number of such functions without any restrictions will be 4 factorial, right? But 4 factorial also includes the case when 1 is going to 1 or 2 is going to 2, and so on and so forth. So I can define again similarly. Let's say n1 represents the number of such functions where 1 is going to 1. Okay, n2 represents number of such functions when 2 is going to 2. n3 represents number of such functions when 3 is going to 3. And n4 represents number of such functions when 4 is going to 4. And remember, we have to find one function. So clearly, we don't want n1 union n2, union n3, union n4. So in such case, the answer should be total number of functions, which is 4 factorial. Why I'm writing total number of functions as 4 factorial, or instead of 4 to the power 4, because 1 is having 4 choice. When I write 4 to the power 4, it includes many 1 functions also, like everyone going to 1. Okay, it also includes this case when everyone is going to 1. But that's not our problem statement. That will be too much size. It will tell like you are in India. First we want to be in Bangalore. Okay, so for that 4 factorial will be total number of injective functions. Among those injective, there is further restrictions that you can't go to your own place. Okay, so clearly this is a problem of dearrangement, but I'm not using the word because I want to solve it from fundamentals. Okay, so 4 factorial is total number of objects minus number of elements in this set. Now this again decodes to 4 factorial minus n1 plus n2 plus n3 plus n4, where this represents number of ways in which 1 is going to 1, number of ways in which 2 is going to 2, number of ways in which 4 is going to 4. So 4 factorial minus this, minus taking 2 at a time. So of course there will be 6 terms. Okay, plus taking 3 at a time. So on and so forth. Minus taken 4 at a time. And that's it. Now we'll just calculate these values. So what is n1? n1 is the cases, number of functions, injective functions where 1 is going to 1. Now if 1 is going to 1, what about the next 3? Again, don't do the mistake of giving 3 choices, because remember at the top of the thing, first you have to Bangalore. We are counting injective functions. So when we have 2, 3, 4, we have objects 2, 3, 4 here. Moreover, when 1 goes to 1, it doesn't matter where 2, 3, 4 goes. Okay. So it might happen like 2 is going to 3, 3 is going to 2, or 4 is going to 4. Everything is counted. That is taken care of in principle of inclusion exclusion. So n1 count is very simple. 1 going to 1. So remaining 2, 3, 4 will have 3 objects, and that they can go in 3 factorial each. Similarly, for n2, n3, n4, by the symmetricity of problem, it will be 3 factorial. Okay. What about any structure when 2 of them is common? So n1 intersection n2. It means 1 goes to 1 and 2 goes to 1. 2 goes to 2. So in that case, we are left with 2, 3, 4, and that has to go to 3, 4 in 2 factorial each. What about 1, 2, 3 going to 1, 2, 3? Now if 1, 2, 3 goes to 1, 2, 3, you don't have a choice for 4. It has to go to 4. So there is only one way. And what about when 1, 2, 3, 4 goes to 1, 2, 3, 4? So there is only one way, because everything is mapped uniquely. Okay, so let's calculate this value. So we have total 4 factorial minus 3 factorial, and since this minus and minus will become plus, so we have 4 factorial minus 3 factorial into how many terms are there? 4 terms. Now minus minus becomes plus. So we have plus. How many terms are there? Having 2 factorial count. out of 4 terms, I have to select 2 of them, 4c2, so which is 4c2 into 2 factorial. Now again minus, how many terms are there having 3 elements, and 1 and 2 and 3 types. So out of 4 again we have 3, and that count is 1 for each, and we have last plus, and that gives answer 9. Okay, so this was really nice. You can use the same method to find the answers for, like 5 objects, 6 objects, 7 objects, and up to n objects. In fact, this answer 9 is known as dearrangement. Dearrangement means destroying the arrangement. So dearrangement is a situation where no object goes to its original position. So this was basically D of 4, which is 9. So in examination, you don't have to do anything. You should remember the idea of dearrangement, which is of course discussed in most of the YouTube channels. My point is to prove it from basics, from 0 level. There is something what to remember. If you'll find D5, it will be 44. Okay, and there is still a nice recursion of dearrangement. You can connect D4 to D5 directly without doing it. So I hope you enjoyed the problem. For J, you could remember D4, D5 value. D3 is directly left an exercise for you. It will be 2, D1. Think of this. What about D2? If you have 2 objects, 1, 2, the only way they can be arranged is 4. So there is some pattern also from D2, D3, D4, D5. So, okay, what is that pattern? Let's say if I think of D5 and D4. So D5 is 44 and D4 is 9. Right. What about D3? It's 2. So we can see D5 is, it can be proved that it's D4 plus D3 times 4. Right. So in general, Dn will be n minus 1 times Dn minus 1 plus Dn minus 2. So using this recurrence, which I urge you to prove, and it's not very difficult, you can directly get the value of D5, because D4 if I know 9, D3 if I know 2, 7 into 4, 44. From here you can get the next element also, D6. That's going to be 5 times D5 plus D4. Now what is D5? It's 44. D4 is 9. So 5 into 53. That will give you 265. So the way to remember D6 is, in a year we have 365 days, so it's less than 100. Okay, it's 265. Now you see, like finding this recursion is not difficult, and let me give a clue for that because it's really interesting. So now suppose you have 1, 2, 3 till n elements, 1, 2, 3 till n elements. So Dn represents when none of them goes to its original position. Okay, so now we'll have 2 possibilities for Dn. Let's consider this point n. So what are the possibilities for n? Either n will go to the position 1, 2, 3, 4, 5, 6, 7 till n minus 1, because n cannot go to n, right? That is not in Dn. So let's say if n is going to 1. Now if n is going to 1, under that case we have 2 possibilities for 1. Then 1 might go to n or 1 might not go to n. So if n is going to 1, we have 2 possibilities, 1 going to n and 1 not going to n. Okay. Now if n goes to 1 and 1 goes to n, clearly we have 2 to n minus 1 objects and 2 to n minus 1 objects. So that's nothing but the arrangement of n minus 2. Right. Now for the second case, when 1 is not going to n. So we have 1, 2, 3 till n, and if n goes to 1, and now if 1 doesn't go to n, so suppose instead of that 1 goes to any other element, 2. Okay, so under this case, what will be the number of the arrangement possible? Now we know the correct position for n was n, so n is not going to n, right? Now 1 should not go to 1, so of course 1 will go to 2, 2 will go to some other object, 3 will go to some other object, and minus 1 is going to some other object. Okay, so now n cannot go to n, that's it. Okay, so under this condition, what we want, if n goes to 1 and 1 doesn't go to n, okay, so 1 should not go to n, 1 should not go to n, 2 should not go to 2, of course, 3 should not go to 3, 4 should not go to 4, and n minus 1 should not go to n minus 1. Now that's very interesting thing, because you can feel it's basically a dearrangement of just n minus 1 object. Why? Because 1 not going to 1, it feels as if I can fool this n and I can treat this to be 1. So it's basically 1 is not going to this place and that place is n. So whether you call it by the name n or 1, it doesn't matter, okay? Because 2 should not go to 2, 3 should not go to 3, 4 should not go to 4, n minus 1 should not go to n minus 1, and 1 should not go to 1, okay? That is the arrangement of n objects. But here we want 1 should not go to n. So for the correct position of 1, we have n, okay? And we don't want to be mapped here. So it's fundamentally d of n minus 1. Okay, so now if 1 is not going to n, it means the correct position from 1 was n, not 1 this time, because this is already locked. So no n and no 1 is there in the picture. So the question is equivalently to, we have 1, 2, 3 till n minus 1 elements, and we have 2, 3 till n. Okay, and now we know 2 should not go to 2, 3 should not go to 3, like this, n minus 1 should not go to n minus 1, and 1 should not go to n. So basically this is equivalent to telling as if we have 1, 2, 3, 4 till n minus 1, and we have, let's say, n, 2, 3, 4, I'm writing this in other fanciful ways, and now n minus 1 should not go there, n minus 2 should not go to n minus 2, okay, 4 should not go to 4, 3 should not go to 3, 2 should not go to 2, and 1 should not go to this place. So I can treat this n to be the correct place for 1. So it's basically what? The arrangement of n minus 1 only. Okay. Now of course, how many ways were there to select for n to go? It could have went to any one of the n possibilities. So because 1 is not a special like n is going to 1. So that's why if when n goes to 1, in that cases, the number of possibilities that we are having is dn minus 2 plus dn minus 1. Now it might happen like n is going to 2, 3, 4, so n possibilities. So total possibilities will be n times dn minus 2 plus dn minus 1. Hence dearrangement of n equals n times dearrangement of n minus 1 plus dearrangement of n minus 2. And this is the recurrence relation. Again a function f, which is from E to P. And this time let me change the set because I've done all the above problem with the same set notation. And P is, let's say, minus 2, minus 1, 0, 1, 2, 3, 4, 5. So set A is having 5 elements, set B is having 6, 7, 8 elements. The first question is we have to find number of a strictly increasing function from set A to set B. Okay, and the second question is we have to find the increasing function, just increasing function from set A to B. So what is the difference between these two problems? So before I go, let me tell you what is the meaning of a strictly increasing function. So you know, for any function f of x, it is known as strictly increasing if given 2 input, the output is strictly greater. So f of x2 is more than f of x1 if x2 is greater than x1. So it's known as strictly increasing function. What about increasing function? Increasing function might be even constant for some place. So given 2 input x1, x2, so that x2 is more than x1. If f of x2 is either greater than f of x1 or equal to x1, so it's basically a little bit more conservative guardianship, then we call the function is increasing function. So we use the word strict in the strict inequality sense, and increasing means even equality can happen. Okay, so first thing first, we have set A containing 5 objects and set B containing 13, minus 2, minus 1, 0, 1, 2, 3, 4, 5. So how many strictly increasing function is there? So of course, for a strictly increasing function, we want if 2 inputs is different, 2 output is also different. So we can't have 1 going to minus 2 and 2 going to minus 2, because in that case, f of 1 will become f of 2, even if 2 is more than 1. So this is not a strictly increasing, right? So one of the answers will be, let's say 1 goes to -2, 2 goes to -1, 3 goes to 0, 4 goes to 1, and 5 going to 2. So this is possible because we want output also to increase when the input is increasing. So clearly from those 8 objects, I can select any 5 of them, and once I have selected any 5, let's say I have selected -2, -1, 0, 1, 2, there is only one way to arrange them in increasing order. What I mean is, let's say someone selected -2, 0, 2, 4, and 5. So -2, 0, 2, 4, and 5. So there is only one way to arrange them, right? Because one will be maximum, other will be second maximum, third will be third maximum, then 0 and -2. So once you have selected, how many ways are there to arrange? Is there only one way? Okay, you don't have a choice, because for any 5 elements selected in output set A2, A3, A4, A5, you can't have any other arrangement of increasing order. So the answer to this problem is very simple, it's HC5. Okay, what about restricted decreasing? It's still HC5, because again, once you select 5 objects, there is only one way to arrange them in the decreasing order. Okay, now the challenge is, what about increasing function? So here we go, and again I'll give you two methods to understand the physics properly. First method is a bit lengthy, but of course conceptual. The second is one-liner solution. So 1, 2, 3, 4, 5, -2, -1, 0, 1, 2, 3, 4, 5, set A, set B. So from the condition of the problem, we want f of 1 should be less than equals f of 2, should be less than equals f of 3, less than equals f of 4, and should be less than equals f of 5, where all these f1 to f5 belongs to this set. Okay, so we'll break this into different cases. That is the simplest idea to start with. So let's say if I take case 1, and all these are distinct. Now clearly under this condition, we have 8 objects in the second set B, and out of 8 I have to select 5 of them, so 8 C5. So this is basically the answer for the first question, number of restricted increasing. Now case 2, when 2 of them is same. Okay, so case 2 I can tell, let's say when f1 is equals f2, and then f3, f4, and f5. So if 1 and 2 is same, one way, right? Because 1 and 2 has to be same. So let's say if 1 is going to -2, 2 has to go to -2. Then 3, 4, 5 doesn't have a choice. It has to arrange an increasing order. But clearly it would have happened when 2 and 3 is same, or 3 and 4 is same, or 4 or 5 is same. So we have 1, 2, f2, f3, f4, f5, and I can put equality at this place or this place. So we have 2 equality, right? And this can be the situation. So when f1 and f2 is equal, that is greater than less than f3, f4, and f5. So for equality, how many positions are there? In fact, we have 1 position, 2 position, 3 position, 4 position. So 4C2. So we have 6 position. And the number of distinct objects I have to select is 1, 2, 3. Because if I select f1, f2, and f3 is fixed. So out of 8, I have to select 3, and then 4C2, which is 8C3 into 6. Now case 4, again we have f1, f2, f3, and f4. So for equality, we have 3 place out of 4, 1 place, 2 place, 3 place. So out of these 3 place, I'll select 2 of them where they can be equal. And we have f5. So out of this 4 place, for equality, out of this 4 place, I can select any 2 place for equality, because for them to be equal, so 4C. Okay, case 4, now we have 4 equality. So let's say case 4, now we have 4 equality. So let's say f1, f2, f3 equals f4 less than f5. So we have 4 positions for equality, 1, 2, 3, 4. At any of these 4 positions, I can select 3 of them to put equality, and the number of elements that I have to select is just 2 distinct elements. Because if I select 4 f1 again, let's say 5, and f5 is 7, so all these will become uniquely fixed once f1 is selected. So out of 8, I'll select 2. and that goes to 4 times 8C2. Now last one, case 5, when you have all 5 equality. So there is only one case, F3, F4, F5. For equality we don't have a choice, but for the number of elements, again out of 8 I can select any one. So let's see one is. So summing all of them is basically we are having 8C5 plus 8C4 into 4 plus 8C3 into 6 plus 8C2 into 4 plus 8C1. And now we can use hockeyistic identity, which is NCR plus NCR minus 1 equals n plus 1. So using this repeatedly, you can clearly see we'll have 8C5, and you can split 4 as 3 times 8C4 plus 8C4, and so on and so forth. You can keep on eating this. So NCR and NCR minus 1 is going to be 9C5. Again, that 9C5 will collide with 3 times 9C4 plus 9C3. So this will become 3 times 9C4 plus 9C3, and that is going to give you 12C5 in total. So this is the answer for this problem using this method. Now there is a clever method 2 of solving this problem. We are having A1, A2, 5 element. Let's say B1, B2, 13 elements. Now what we can say is, if you want number of non-increasing functions, so let's say one such situation where A1 is going to B1, A2 is also going to B1, A3 is also going to B1, and so on and so forth. Maybe A5 is going to B2. So we can think in terms of number of connections. Number of connections. Okay, so let's try to get another one-liner solution for this. We have 1, 2, 3, 4, 5. And then -2, -1, 0, 1, 2, 3, 4, 5. Let's try to write one of the sample function, which is an increasing function. So maybe 1 is going to -2. 2 is also going to -2, 3 is going to -1, 4 is going to 2, and 5 is going to 3. So it's also is an increasing function, right? Okay. So what we have seen here, if I try to calibrate this with respect to set B, okay, so -2 has how many connections? -2 has 2 connections because it attached to 1 and 2. What about -1? It has got 1 connection, which is 3. What about 0? It has got no connection. 1, no connection. 2 is having 1 connection. 3 is having 1 connection, which is 5. 4 is not mapped to anyone, and 5 is not mapped to anyone. So you see 2, 1, 0, 0, 1, 1, 0, 0 is a coding for this particular answer. It doesn't make much sense. So let's try to write one more sample example. -2, -1, 0, 1, 2, 3, 4, 5. Let's say this time everyone goes to -2 except 5 going to 2. So now -2 is having how many connections? 1, 2, 3, 4. -1, 0. 0 is having no connection. 1, no connection. 2 is 1 connection. 3 is no connection. 4 no connection, and 5 is no connection. So the entire idea is basis of counting this is based on number of connections that output set is having. Now we know, since it's increasing functions, so if suppose we have a coding 4, 0, 0, 0, 1, 0, 0, 0, what does this mean? It means every element in the same order, which is -2, -1, 0, 1, 2, 3, 4, 5. This is having this many corresponding connections. Yeah, because we have, let's say, first object will have x1 number of connections, second is having x2 number of connections, x5 we have x8 number of connections. So what we can feel is, suppose if -2 is having x1 number of connection in general, because it can have 0 connection, 1 connection, 2, 3, 4, 5, x, and the second element -1 is having x2 number of connection, 0 is having x3, let's say 5 is having x8 number of connection. So in total, how many connections we can have? X1 plus X2 till X8. We'll have 5 connections, right? Because total number of connection has to be 5. If you add all this, 4 plus 1 is 5. If you're adding this, 2 plus 1 plus 1 plus 1 has to 5. Because total number of connections is preserved and conserved. Now, how many connections X1 can have? It will definitely have more than 0 connection, right? So it can have 1, 2, 3, 4, 5. So X1 must have more than 0, less than 5. What about X2? More than 0, less than 5. Similarly, X8, more than 0, less than 5. Okay. Now, of course, this restriction is same as taking X1 greater than equal to 0, X2 greater than equal to 0, and X8 greater than 0. The reason being, there cannot be any solutions for these equations, and okay, which is basically non-negative integral solutions to these equations for which any of the element is more than 5. Let's say if X1 is 6, then it's not possible. Even if all of them is having 0, 0, 0, it cannot go to 5. Okay. So this external restrictions or one-sided restriction of less than 5, we need to divide this 5 into 8 parts. So let's come with, and this is a very external problem, a star bar technique, which gives number of answer as 5 plus 8 minus 1, C8 minus 1, which goes to 12C7. And this is exactly the same answer that we got for the above case. Now, some of you might be wondering how 12C7 is same as 12C5. Indeed, it's equal because NCR is NCM minus R.